Hello everybody. We're still talking about the unsteady state molecular diffusion in finite medium, and we have been discussing the parameters that we will use in the chart, and we have here the three parameters that we discussed: the parameter that represents the concentration, the parameter that represents the time, the dimensionless parameter that represents the position. And we have mentioned this last parameter, which is the relative resistance, but we have not gone into the details of this parameter. What does it mean and why we need to use this parameter? And to understand this, let's take a look at this image here, or this photo here. So this is the gray area here represents the body where the diffusion takes place. This dotted line is the axis of symmetry, and this is x and this is x1, which is the distance from the axis of symmetry to the outer surface of the body. And as we mentioned earlier, for the dimensionless concentration, that it's function of the concentration on the surface and the concentration Ca node, which is the initial concentration, and that we use these two variables to calculate the value of concentration based on the value of y that we got from the chart. But actually, in many cases, the value of CAS is not a practical parameter that we can use. It's the concentration at the surface between the body where the diffusion takes place, which could be mainly a solid body, and the surrounding environment, which in most of the cases is fluid. It's air, it's water, whatever the fluid or liquid, whatever the fluid it is. But in general, you have convection outside the body. So the species diffuses from inside the body to outside, and from the outside to, or from the surface to outside, by convection. So there is a concentration in the bulk of the fluid phase, which is called Ca infinity, which is the concentration in the bulk, and there is the concentration at the surface. Practically speaking, it's not possible to get the concentration at the surface. This is not a possible thing to do. We cannot do this and get an accurate value of it. So we can get the bulk concentration, but not the surface concentration. And this means that we have two types of resistance for the mass transfer. One of them is the resistance inside the body, the resistance to molecular diffusion, and there is the resistance to convection outside. So the relative resistance is the diffusion coefficient divided by Kc multiplied by x1, which can be rewritten as 1 over Kc divided by x1 over dAb. And this Kc is the mass transfer coefficient, and 1 over Kc is the convection resistance. It's 1 over the heat transfer coefficient, the mass transfer coefficient. So this is the convection resistance. So if you have very high or very quick mass transfer in the convection part, there is very low resistance, then you will have a very large value of Kc, so the resistance is very small, and vice versa. So this represents the resistance in the convection outside the body, the external convection, and this x1 over dAb is the internal conduction, or the body conduction. It's molecular diffusion, it's the body molecular diffusion resistance. So this is the value or the meaning of M. So why it's important? Because we want to use the concentration, which is C infinity, instead of CAS. This is the practical value that we can get, we can find. So if I use C infinity, then in this case I have a problem, because I'm substituting in the y equation with a concentration which is not the right concentration, and that's why we have this value of M, because M represents the adjustment of the value of y based on the ratio between the two resistances. So and as we said, it's a relative resistance of the diffusion mass transfer to convection mass transfer, and in case I have very low resistance in the convection, if you have a lot of turbulence and the convection resistance is very low, then M is gonna be almost close to zero. And in this case, we will have no resistance here, which means that there is no driving force either. So CA and CES and CA infinity would be the same. So we have two cases for this M. Either you have no convection resistance, in this case CAS equals CA infinity, and then the equation is gonna be the same. And instead of having CAS, I'm gonna use CA infinity. In case I have a value of M which is not zero, if I have a positive value of M, which means that there is a resistance to mass transfer outside the body, at a convection mass transfer resistance, I mean. So in this case, we will use the same equation, but which is C infinity minus CA and C infinity minus CA node. But in this case, the value of M will shift the curve that I'm using somehow, and this is something that we will see next video, inshallah. So this is something that M will take care of. So we're still gonna use the same form of the equation for the two cases, for M equals 0 and M equals more or it's more than 0, but the value of M is gonna adjust the difference between CAS and CE node in this case. So there is one related thing here which is called Biot number. The Biot number is a dimensionless number, which is the internal resistance to diffusional mass transfer divided by the external resistance to convection mass transfer, which is 1 over M. And it's defined as KCL over D. KC is the mass transfer coefficient and D is the diffusion coefficient, of course. And I wanted to highlight it here because there is another dimensionless number that we will see in the next chapter, which is very similar to this. It's almost the same thing. It's KCL over DAB. It's the same formula. But the difference between the Biot number and the other number, which is Sherwood number, is that Sherwood number considers K and D for the same medium. So KC and D are both for the fluid phase where convection is taking place. But here for Biot number, the KC is for the fluid phase, D is for the body where the diffusion is taking place in. So it's a very important difference to not get confused between these two dimensionless parameters. So in summary, these are the parameters that we have. We have Y, X, N, and M. Using these three parameters, you can go to the chart and get the value of Y. And from the value of Y, I can calculate the value of CA. The exact same chart can be used for heat conduction as it is used for molecular mass transfer diffusion. And this is almost the same formulas for all of them, except for the molecular diffusivity. Here it's thermal diffusivity. Here it's the diffusion coefficient. Here it is the heat transfer coefficient. I mean, it's the thermal conductivity, I'm sorry. And for the mass transfer coefficient, we have the heat transfer coefficient. And for the concentration, you have the temperature. So it's almost the same. You just put the parameters that are suitable for heat transfer instead of the parameters of mass transfer, and it's going to be the exact same thing. So this is all what we need to do about the parameters that we use in the charts. In the next video, inshallah, we will talk about or we'll see the charts and see how we can deal with them and solve an example about the unsteady state molecular diffusion in finite bodies using these charts. So I'll see you then, inshallah. Goodbye.